All right, so the title of my talk here is Software Vulnerability Discovery and Exploitation During Red Team Assessments. I just kind of realized that this is actually the longest, least sexy name for a title ever, so you'll have to bear with me. Hopefully it'll prove to be worth it. Let's see, so give you a little background about myself. I work here in Charleston. I'm a red team operator. Our job is pretty much to simulate real-world attacks against our customers' networks, so that hopefully we can find vulnerabilities and tell those to our customers so that they can patch these. I've been doing this probably for about 3 or 4 years now, so our job continues to get a whole lot harder as our defenders, our blue team, is getting a whole lot better. Because of that, we started to look into other possible ways that we can have success on our team and actually be able to find some of the harder avenues that maybe some of the more advanced attackers are starting to use nowadays. And one of these areas that I've been looking into a lot now is actually vulnerability research. So we're looking for actual bugs in some of the software running on the systems that we're running across. And one of the main reasons we're doing this is because a lot of our assessments are actually long-term, persistent red team assessments. So we might actually have access inside a network anywhere from 6 months to a year. And once we're inside, the reason we're in there is we're also trying to test them for your internal vulnerabilities. And so we usually have to set up persistence inside the network, and then our biggest goal next is usually try to move laterally throughout the network. So that's kind of where this all comes into, is we're starting to look for services and these types of things that might have vulnerabilities that we could use to propagate throughout the network. All right, so I guess the where to start on this is I just want to present just a lot of the tools and the ways that we start looking for these targets. And a lot of these you guys are probably pretty used to. And so a lot of this talk is really just going to be collecting those all together so that you can package it up and kind of have a process. Our first step, typically when we get on a box, the first thing we would want to do if we were looking for remote access opportunities is the first thing we do is we run netstat if it's a Windows box. We start identifying what sockets are open, what processes those are running on those sockets. As you can see from our example here, this is just a quick example. We'll see if something's running on port 902, and we see that that's process 2352. From this point, we probably want to identify, okay, well, what is that process? Where is it? So I can identify what the application is. Your next step in that would just be run task list. We pass it in that process ID, and we can see from this example that that's actually VMware. The same process applies to Linux, it's just a little bit different commands. Netstat's the same, but then once you figure out that process ID, you move on and you just search your process list and grep for that process. This particular example, we were just on Kali and we had a listener running, and so it shows us that that was actually Metasploit running. Once you've identified that application and you've found it on a system, keep in mind, like I said, this is assuming that you're already on a system that you've compromised. So more than likely you're going to have a rat or some kind of way into that network. So once it's, like I was saying originally, you're going to get that binary, you're going to download it back to your system, and you're going to start doing analysis on that application. And some of your typical tools that you can use or for your reverse engineering would be IDA Pro or Hexrays. For those of you that have Mac boxes or Linux, you can use Hopper. Pretty much open that up, and from this point you would actually start doing your stack analysis, looking for these entry points for where that data is coming in so you can start trying to trace through the code. When you start that process, like I said, a lot of the places you're going to want to look is where that input comes in. Some of those examples would be, command line parameters, your sockets, as we'd mentioned before, any kind of file reads, environmental variables. Some of those functions that do that kind of thing that kind of stand out, as you probably have seen in things like read, gets, fread, receive from. From here, this is pretty much how it comes in, and at that point, you're going to move directly after that, because typically once that data gets in, it immediately starts getting processed and parsed, and a lot of times those bugs that we end up finding are right in those parsing routines, pretty close to where that data comes in. All right, so as I mentioned, the parsing functions you typically come next. A lot of the vulnerable functions that you guys have probably heard about before when dealing with memory are some of these examples here. These are things to kind of keep your eye out for. If you run across these are definitely hot areas to just make sure that whatever they're doing with memory using these are secure, because a lot of times it's just not recommended to use these. So if you see them, it's definitely something to research further. Make sure, especially if you see anything like custom memory operations and they've written their own string copy or their own memory copy, those are definitely places you want to look closer to make sure they did everything correctly, bounds checking, all those types of things. Another definitely good place to look when you see data being moved around is a lot of times when you have data coming in from the outside, a lot of those protocols will allow you to specify indexes into memory. So say, this is my first record, this is my second record, and a lot of people will actually use those to directly memory access. So if you see any kind of operations coming in from the outside and they're using indexes and you control that, that's always a very interesting thing to look at. All right, so once you've kind of done the most static analysis you can, you typically want to move forward and get into more of a dynamic analysis kind of phase. In order to do that, it takes a lot more time. Static analysis is definitely easier because all you really need is the binary. With dynamic analysis, you actually have to model your environment. So you have to set up your system as closely as possible as the one you found the application on. That means getting whatever libraries it needs, whatever files that it might use for input files, registry keys, if it's Windows, a lot of those fun things that actually make this application run if you were to just kick it off. Luckily, sysinternals gives you tons of tools that actually help this out a lot. So once again, if you're on a system that you've compromised and you're pretty far under the radar, a lot of times you can actually put these tools on there and actually find out what you need to actually create your modeled environment. All right, another option, and this usually comes a little bit further in your analysis, but if, say you're trying to run your application on your modeled environment and for some reason or another it's just not working, one option you could have, and it's definitely easier on things like Linux because GDB comes packaged in, you can actually attach yourself to those processes and dump that memory. At which point then you can take that dump and whatever you have in your modeled environment, and you can actually analyze the two and make sure that, that they're the same. This is definitely one of those things where I've run into the problem where you have one that you feel like you've modeled perfectly, but for some reason or another it just won't run. So you can dump that memory, analyze the two, and see if you missed a library, if the memory addresses are just slightly different, or something like that. Another thing that you'll also notice when you're doing this, if you're on a system, say it's a secure system, you might actually see other HIDS application running like HBSS or EMET or something like that, and that's a good thing to know once you take this further and you're actually trying to write an exploit or something like that. I guess once you get past that point, let's say that you've already found your bug, you've already moved forward, and you've already written an exploit, and once again, like I just mentioned, it's not working for some reason or another, and say it's crashing. So you've done your memory dump, and you still can't figure it out. If you're on Windows, you're on Linux, there are actually abilities to actually turn on the collection of memory dumps from a crash, and you can actually bring those back and analyze those further. So you can see in Windows, it's just a simple registry key. If you have the ability to write to the registry, on Linux, same idea. It's just a quick command, and then those will dump your cores, and you can bring them up in GDB and see what might have gone wrong. All right, from here I kind of want to move into a case study of something that we found when we were doing one of our red team assessments on a system, and we went through the same process that I just described, and I kind of wanted to show you what this might look like in a real world environment. This particular application is called Medicine Serve. It's a medical application. You can actually get it on the internet. A lot of EMR systems use it for storing medical data and these types of things. And so when we found it and we found it running, we thought this might be a pretty good target to start looking at. As you can see, we started in the same process as I originally said, where we ran netstat. We found that it was running on port 8080. We saw the process it was running, and kind of went from there. Once we saw, like I said, what the process ID was, we identified it as the MedServe application. We saw it was running as a service. So our next step was to try to figure out where on this system it was. So we ran SC query, which actually will list, information about any kind of services running on Windows. We were able to figure out where it was on disk, tracked it down, and were able to download it and bring it back. All right, so once we brought it back, we opened it up into IDEA Pro, which is one of our favorite dissemblers. We were lucky enough to actually have Hexray's decompiler. So it makes the code look pretty much like C, allows you to, pretty much reskin all of your variables to what you think they are doing. So by the time you get done, it looks really close to probably what the code looked like when they first wrote it. As I mentioned, the very first thing I did, since I saw that it was running on port 8080, I knew that it was listening in on some sockets. So I looked for any receive functions, and I was lucky enough to find that there were only 2. So all data coming in was coming in through this one function, and then it was probably being processed immediately after. So as you can see, it pretty much takes in a header, and then after it took in the header, it took in the data. Going from here, we assumed, once again, that the function calling this, we were hoping that immediately afterwards it would probably process that data. And we got lucky, and that was exactly what it was. So pretty much it took in the data and then immediately took one field out of that data, which we assumed was the command ID, and began switching over all the different types of commands and processing them accordingly. So when we were looking at this code, as you can see here, it was literally like 300 different commands, and then just how they were processing them. Unfortunately, at this point, this is where it gets really tedious, because we now had 300 commands, and we didn't know which ones could be good, bad, or indifferent, which ones might have bugs, which ones might not. So pretty much at this point, there was a lot of reversing, there was a lot of just fuzzing, just seeing, okay, maybe we can pick the needle out of the haystack, because we didn't want to actually have to go through every single one of these functions, because we were hoping to have a pretty quick turnaround so we could actually use this in our assessments. So much reversing later, we came across this one function. It was a message type. It was like 239, something like that. And it took in our data. And as you might be able to tell here, we had a location on the stack that was expecting 100 integers, at which point it would go through the data that came in, and it was assuming that that data that we gave it was literally an array of integers followed by commas. We don't actually know what they were doing with it. At our point, it really doesn't matter to us. The big thing that stood out to us was that in our loop right here, we have absolutely no bounds checking. So we know it's taking in 100 integers, and the way that it breaks out of this loop is basically when it gets to the end of our array, which is absolutely horrible. So from here, anything over 100 integers is going to override our stack, and we could immediately gain control of this application. At least this was our assumption at this point. All right, so going forward now, we think we found a bug. So we've done our stack analysis. We want to verify this, and this is kind of where you step into your dynamic analysis. It's like, can I actually validate that what I think I saw is actually real? So this is where we started bringing up the tools that I mentioned earlier for dynamic analysis to start identifying what files that application needs, what library it needs, so that I can actually run this on my virtual environment. First thing we did was run list DLLs. That should show us any kind of libraries that it needs to run. As you can tell, there was absolutely nothing proprietary. All the other libraries that it used were all Windows libraries, so this was actually really convenient. Going forward, we did handle.exe, which is another sysinternals tools that just lists any open handles to any files that it might have open at the time. This is a good thing if your application opened a bunch of files and left them open. Unfortunately, this isn't going to show anything that it might open as a configuration file and then close it subsequently. Lucky for us, though, we got a good amount of files that it kept open, and it looks like we had a log file, because anytime you see a document or a text file or something like that, that's probably a log. So our next step was to just go ahead and open up that log file and see what that was. From the log file, we actually can glean there was a few other files that it needed. But the kind of overarching thing we saw was pretty much everything it relied on was in the directory that the binary was in. So we were hoping we just copy that install directory, and that would be pretty much everything. So we got just about everything. So we got all the files over that were libraries. We got all the files over that were input files. We still weren't having much luck getting it running. And we remembered the one last thing we didn't check was the registry for the actual service. And it's pretty rare, but sometimes you'll actually see them put data in there for their startup stuff. And so we checked it out, looked at the registry, and noticed that they actually had the path to where their data was. So that wasn't hard-coded. And so once we got that out and put that in our system, we were able to start the application up and begin our dynamic analysis. As I kind of mentioned, when you're setting up your dynamic analysis, modeling, virtualized, whatever, you actually want to get to where everything is as close as possible to what you're looking at. So you want to get the same operating system, same patch level. You want to make sure your registry looks the same. You want to have debugging tools so that you can actually step through things if you need to. You want to have some way of writing scripts, because more than likely you're going to have a proof of concept that you need to work on to quickly send data at this thing without much work. And once you've done that, you're going to want to try to match what you found in your static analysis over to a debugger, because you're pretty much going to start switching tools at this point, unless you do use a debugger immediately from your disassembler. For example, IDA Pro has a debugger, but a lot of times I actually tend to move over to Immunity debugger because they have a lot of built-in tools that are really nice. So from this point, we pretty much found the idea or the address of the function that we thought was vulnerable, copied that thing down, and then moved over to our debugger and put in a breakpoint. At this point, now we have our system set up the way we want it. We have our binary on it. We've loaded it up in our debugger, and we're ready to develop a proof of concept to exercise what we think might have been a bug and see what happens. So once we, like I said, get to this point, we kind of start thinking about the design for our proof of concept. From what we've seen in our disassembly, there's a header, there's data, and there's the data length. So we should be able to go ahead and start getting a proof of concept for a lot of the boilerplate stuff. We don't really know, like I said, what that function might be doing otherwise, or what we might have to do to make it a reliable exploit or anything like that. That's going to come much later, but we should be able to go ahead and set up the necessary things like opening a socket, sending and receiving, closing that socket, just the really easy stuff that will get us to the next step of being able to develop a proof of concept. And you can choose whatever scripting language you feel better about doing this kind of stuff in. I usually pick Python just because I'm used to it. Here was our first stab at our little proof of concept skeleton. You can see it just takes in the host, the port, creates a socket, creates a string down here that's literally just an array of ones followed by commas. And then it just sends it, and then it closes it. We did actually add a little helper function over here that will set up that initial header. It would just basically say, hey, this is the type, this is of the function that we're going to want to exercise, and this is the length of all of our data. So that just kind of made it a little easier for us whenever we sent data to this service. All right, so we got really lucky, and even with that very simple proof of concept, you can see that when we ran it, we immediately got access over EIP, which is your instruction pointer, which is pretty much the one register that determines where your next execution is going to be. And as y'all could see earlier, there was that array of ones, and we have a 1 sitting in EIP. So we got really happy at this point because this is ideal. From this point, you probably want to start thinking about, okay, now I have EIP, I would like to actually put some shellcode in there, I want to take over the system, I want to use this exploit. And when you start thinking about those types of things, you want to know, again, more about your environment. You want to know, what protections does this binary have in place? What am I going to have to get around to make this work? In our case, we already know, because we control EIP, that there were no stack canaries, which is typically, it's a protection that keeps you from being able to get to your instruction pointer. Because if it overwrites that stack canary, then it checks it before the end of the function, and then it will kill the whole program before you even get to the situation we just saw. So we know it doesn't have that protection. From our list here, this is actually a command that you can run from a Mona script, which is developed by Corlan, that will tell you all the protections for every application, every library that you have loaded into memory at the time. And as you can tell from ours, it actually shows that our binary right there in the middle has absolutely no protections. This is, like, once again, ideal for us, horrible for them. So at this point, we literally could have just written one instruction to our EIP register and jumped straight to our shellcode. And we did try that at first, but we assumed that more than likely the systems we were dealing with, which were actually very secure systems, probably at least had DEP turned on at the operating system level. And so we determined that probably to make this as reliably as possible, we would go ahead and pretend like all the protections were enabled and write an exploit for that. Let's see. So going with that assumption in mind, we're assuming that we have to get around DEP, which means that I can't execute anything directly on the stack. So typically the first thing you want to do is you want to put shellcode on the stack and you want to execute it. So we can't do that. And we also can see that other than our binary, ASLR is enabled as a protection too. And ASLR, basically all that means is whenever you load up your binary, it gets loaded in a different place in memory. And so when we are actually writing these exploits, your exploit's going to be static unless you have the ability to leak addresses back to you. In our case, we don't even need that. So we want to actually be able to just have static addresses in our exploit, which we can jump to, and we'll actually start executing down till we get to our shellcode. So in this particular case, as I said, we're going to try to pretend as if all these protections are in place. So with them in place, we're actually going to have to make calls to re-enable execution on our stack. Lucky for us, Windows provides lots of different ways to do that. You can use write process memory, you can use virtual alloc, and the great thing about this Mona script as well is it will actually look for those gadgets for you, and it'll just construct that whole chain for you. So on this slide right here, you can actually see what happened when I ran the ROP chain command. It went ahead, it found every gadget I need, which is, when I say gadget, this is actually an address in a static library that you can use to do something you need. In this case, what we need to do is set up our stack in a way to call that function. So this particular chain is set up to call virtual alloc. It basically sets up all the parameters needed for virtual alloc, and then once we call virtual alloc, it will change our stack from non-executable back to executable, at which point we can jump straight to our shellcode and start executing. The only problem I found in our particular example was that script found gadgets to every single thing we needed except the address to virtual alloc. So it's kind of a big problem because that's, what we're all hinged on here. So going forward, we realized we're going to have to resolve virtual alloc ourselves using 2 additional function calls. The first being get module handle, which will give us the address to kernel 32. And then once we get the address to kernel 32, we need to find the address of get process address so that we can then resolve virtual alloc. And then, of course, once we get the virtual alloc address, we drop straight into this ROP chain that was generated for us, and then our shellcode. So since all this gets a little confusing, it really comes down to, just software design in the end. And so you start designing out what this is going to need to look like, and then you can start plugging in the pieces as you get to them. So right now in the process, we pretty much have our packet header set up. We have all of our ones, which is basically our garbage there. And then we'll start setting up our ROP gadgets for the 3 stages that we needed. That first being getting the module handle to kernel 32, then getting the address to virtual alloc, and then calling virtual alloc, and then calling our shellcode. We added one extra little helper function. Since we were actually passing in that data, it's looking for strings that are numbers. And when we end up having our shellcode, it'll typically just be raw. So we're just going to have a bunch of raw bytes. And we need to format that in such a way that they just look like an array of numbers. So all this function does is take in all of our shellcode, and it converts them into an array of numbers and adds them to the end of our data segment there. All right, so let's have a demo. All right, so before I run this, I'm going to show you kind of what it ended up looking like. So this is our code. This is our proof of concept. Let's see if I can zoom in. Oh. Y'all probably can't see this at all, can you? Okay. Just bear with me. All right, so this part up top is all of our shellcode, and this is basically just shellcode for a reverse TCP from interpreter. And as you go down, this is our send function that basically just sets up our header and then sends our data, as we were talking about. This is our little helper function that turns our shellcode into the array of numbers. This is a similar helper function just for strings. And then this is actually our ROP chain. So that first one, as we mentioned before, that's going to call get module handle. It's going to get kernel 32. As you scroll down, we'll have our next call, which will be get process address. And then as you keep going, we're finally going to get down to our actual ROP chain to call virtual alloc. I think that's right here. And then once we call virtual alloc, the last thing we do, which would be right here, is add our shellcode. All right. So, all right, so if you look over here, we just have a simple multi-handler waiting for a callback on port 444 for a reverse TCP payload. And let's see, where did my mouse go? And if we look at our box here, let's make sure we have this service running. All right, so let's check that port. So we can see we have a service listed here on port 8080. That is that medicine serve that we just we've been talking about. And if we run our script, can look up here. Looks like we got a shell back. At which point we can make sure. Yeah, y'all definitely can't see this. I barely can. We see that's we are system, and if we run our system info, we see this is our Win7 box. So at this point, this would be exactly what we wanted. This is, we found a service, we were able to write an exploit, and now we're hoping that this service would be installed all over the network, and we'd be able to laterally propagate and start setting up our persistence on other boxes that we may or may not could have gotten through in our red team assessment. All right. So, one of the fun things about stepping into this new type of work in the stuff that we do, as we just described, all these things that we're finding are considered O-days. So a lot of these people don't know what we found. They don't even know that this stuff is running on their systems. So, you know, it's a gray area, and you definitely have to make sure that the customers that you're working with are completely okay with you doing these types of things. And lucky for us, our customers, they want to know about anything possible that can be done to their network. So they're completely okay with this. But you have to make sure that you're not going to be doing anything that could bring down their networks. So when you start doing things like writing exploits, you need to test a lot. And you need to make sure that what you're doing isn't going to be adding anything negative to their performance or anything like that. In this particular case, it was pretty simple because once we got on, we immediately restarted our service, and they didn't even know that we had done anything. Make sure you get permission, and then of course once you get permission, then you just get lots of shells. The next step, of course, knowing the ramifications of what you've just done, you pretty much have to realize, all right, well now I got to start telling people what happened here. And a lot of times it's a lot further up the chain than what you think, because a lot of times your customer can't do anything about this. So what we've noticed is, depending on the customer and how widespread it is, if it's commercial based, you can pretty easily just go to US CERT and say, hey, I found this thing with this vendor. We think it's bad news. Could you reach out to them for us and start this process? Because in our experience so far too, like a lot of these vendors, they don't want to talk to you. And you can try pretty hard, but we've been ignored pretty much every time we try to talk to vendors so far. But luckily US CERT somehow gets them to talk back, and they start actually moving forward, which is great. If you can't, let's say for example that this isn't commercial, this is actually just GOT software. You can also have other avenues like Cybercom, for example, and they will push through similar things, and they will keep it more close to the chest, since a lot of that stuff might be sensitive. There's also MITRE and NIST. I think they all pretty much work together with US CERT as the main reporting group, at which point they will then replicate those disclosures to, you know, the others. All right, does anybody have any questions? Anyone? All right, well, that's all I got.